Okay, we are going to continue with where we left off. We started talking about exponent rules, and we talked about what it looked like to have a base with a power. We also talked about the fact that every base has a power, and if there isn't a power recorded or written, you know that that power is a 1, that exponent is a 1. All of the examples that we've seen so far, they're in the exponent rules section, they're one-term expressions. Okay, it's one term. You know that there will be multiple terms if you have addition or subtraction separating them, but we don't have that. So our focus is looking at the one term, and when it has exponents and the things we're trying to do with those exponents, we have to apply specific rules. So let's take a look and continue with where we left off and see how it goes. As a recap, for this first example, we have 2x to the fifth, y to the third. The 2, the x, the y, those are all my bases, and they each have their own respective power. Same thing with my second example, 10a to the fourth b over b squared c. My 10a, b, c, those are all bases, and again, they each have their own respective power. As we dissect these, be very careful that you don't combine the 10 and the a and say, oh, 10a is being raised to the fourth. That's not true. The 10 is being raised to the first power. The a alone is being raised to the fourth power. Every base will have its own power. So let's turn the page and see some rules in action. Let's start with the product rule. So for the product rule, I made a note here, and I kind of want you to chant that to yourselves. Keep the base, add the powers. Keep the base, add the powers. For the product rule, what this says is that when you are multiplying these single term expressions, if they have the same base, you're going to keep the base and simply add the power. So generally speaking, take a look. When we have x to the m times x to the n, all we have to do is keep the base, which is x. And notice it doesn't become 2x. Notice it doesn't become x squared. You literally keep whatever that base is, and you simply add those powers. So m plus n becomes the new exponent. Okay, so let's take a look at this example. Notice here for this first set of parentheses, we have 1, 2, 3, 4, 5 x's. We know that x times x times x continuous, this particular expression here can be rewritten as x to the fifth. When you have y times y times y, you can rewrite that as y to the third. Notice we have z times z, and we can rewrite that as z squared. So that's what goes in my first set of parentheses. In my next set of parentheses, I have x times x, so we can rewrite that as x squared. We have a y, and I could write that as y to the first power, if that makes things a little bit more clear for you. And then z times z times z, well, we'll write z to the third power. Now, according to the product rule, you're going to keep the base and add the powers. And notice here that product means multiplication, correct? And notice that we have x to the fifth times y to the third times z to the second times x to the second times y to the first times z to the third. There is no distribution here. We do not have we do not have more than one term in this set of parentheses, so we're not distributing. We're essentially combining the bases. So x to the fifth times x to the second, well, these have the same base. So you're going to keep the base, add the powers. Keep the base, add the powers. So it becomes x to the seventh power. With our y's, you're going to keep the base, add the powers. So this becomes y to the fourth power. For our z's, you're going to keep the base, add the powers. You're going to hear it enough times where you're just going to end up saying that to yourselves. Let's do this again. Notice here we have 1, 2, 3, 4 factors of 4. So we can rewrite this as 4 to the fourth power. And I'm actually going to write on this side. So we have 4 to the fourth power. We have m to the second power. We have an n, and we have a c. So n to the first, c to the first. Isn't it kind of nice seeing it broken down this way? the whole point of me breaking it down this way is so that you can see the translation. So you can see what it looks like when we actually expand it. And then when we put it back together. In our second set of parentheses, we have 4 to the first power, m to the first power, n to the first power, and c to the second power. Now that everything has been grouped together, so it's easier to see, so it's more compact, now we can apply the product rule, meaning keep the base and add the powers. So we keep the 4 and add the powers. 4 plus 1, 5. Keep the m, add the powers. 2 plus 1, 3. Keep the n, add the powers, we get 2. And keep the c, add the powers, and we get 3. And there you have it. That's all that you have to do with product rule. Now, what we're about to see are a bunch of examples applying the product rule, but I don't want you to think that you're not allowed to expand. So for instance, 4 to the 5th power, let's take a look. If I took 4 and I raise it to the 5th power, I get 1024. So we can actually rewrite this answer as 1024, m to the 3rd, n to the 2nd, c to the 3rd. Okay, since that was manageable. But what if you had something like 4 to the 11th power? Take a look at that number. I would rather you leave it in exponential form than actually evaluating it. But that comes on a case-by-case basis, and I think the more you see, the more you'll recognize, okay, let's leave it in exponential form versus actually evaluating it. On any assessments, it's going to be very clear what the expectation is, so don't panic. Let's take a look at our first problem. So we have 10x to the 5th, y to the 3rd, times negative 2x to the 3rd, y to the 8th. If it makes you feel a little bit better, we can look at the variables first. That's totally up to you. We could totally do the variables first. Let's do that. I'm going to leave the 10 and the negative 2 on the side for a moment. We have an x to the 5th and an x to the 3rd. Keep the base, add the power. So we know that that becomes x to the 8th. I have a y to the 3rd and a y to the 8th, so we're going to keep the base and add the power. So that becomes y to the 11th. But notice we still have a 10 and we have a negative 2. Notice that the operation that connects them is multiplication. So wouldn't it suffice to say 10 times negative 2? There are no powers outside of 1. A 10 to the first power is just a 10. And negative 2 to the first power is just a negative 2. So 10 times a negative 2, well, that just gives us a negative 20. And there's our answer. Negative 20, x to the 8th, y to the 11th. It's literally as simple as that. Let's look at number 2 and try that again. Again, if it helps, let's start with the variable terms first, or the variable bases first, and then we'll take a look at the numerical parts, the numerical bases. So we have a b to the 12th and a b to the 6th. Keep the base, add the powers. So that's going to be b to the 18th. We have a c to the 5th and a c to the first power. Notice there is no exponent written for the c, but every base has its own power. So we're going to write in there a 1, just so that it's clear. So we have c to the 5th times c to the 1st, which is keep the base, add the powers. Then notice we have d to the 4th. There is no other d to combine it with, so it stays d to the 4th. Now, let's deal with the numerical bases. We have a negative 11 times a 4 squared. Now, that's interesting. Way back when we first learned about the order of operations, if we had negative 11 times 4 squared, all of you would tell me that exponents comes before multiplication, that the order is that you must apply the exponent before you multiply. So if I want to take a negative 11 and multiply it by 4 squared, I must first find 4 squared. If we take this 4 squared and we rewrite it, we get 16. So now I have a negative 11 times 16. Perfect. That's what you're looking for in this case. If our base here were another 4 and it was raised to another power, then you would take the 4's, you'd keep the base, and you'd add the powers, much like we did in our previous example. Notice here we have 4 to the 4th times 4 to the 1st. Keep the base, add the powers. Cool. But this is a different base. So negative 11 times 4 squared, or negative 11 times 16, that'll give us negative 176. So my final answer is a negative 176, b to the 18th, c to the 6th, d to the 4th. Okay, let's do it again. Again, if you would like, we can start with the variable base first. So we have an m to the 9th. And notice we have an m here, there's no power written. So we're going to write in here that m is being raised to the first power. Whenever it's not expressed, you know that it's a 1. So m to the 9th times m to the 1st, well, that's just m to the 10th. Then we have n to the 2nd times n to the 3rd. Keep the base, add the power, so n to the 5th. Now let's look at the numerical base. We have an 8 to the 3rd times an 8 to the 7th. Oh, they have the same base. So you're going to keep the base, add the powers. 8 to the 10th. We're not going to overthink that. Let's take a moment to punch in 8 to the 10th in our calculators and see what we end up with. 8 raised to the 10th power. Whoa. We're going to leave it in exponential form. Okay, that is a pretty massive number. So we're going to leave our answer in exponential form. Good, and we're done with the number 3. Let's do number 4 together as well. Notice here we have negative 2 to the 3rd, that's interesting. M to the 5th n, this n is being raised to the first power. Then we have 5 times m to the first power times n to the 2nd, okay. Then we have a negative 3 squared times m to the 3rd times n to the 4th. I like our strategy of working with the variable bases first. It might alleviate some of that stress of trying to evaluate. So let's start with the variable first. M to the 5th, m to the 1st, m to the 3rd. So keep the base, add the powers. 5, 6, 7, 8, 9. And Keith, you asked a really great question. And actually, so for instance, Keith asked this question. I'm going to write in here, example. He said, what if that 8 were negative? So for instance, what if we had negative 8 to the 3rd? I'm not going to rewrite the variables because really that's not the point. Keith asked a question pertaining to my base 8. Okay, we have negative 8 to the 3rd times 8 to the 7th. Okay, recall that we learned that this power, because it's not outside of the set of the parentheses, this power is only associated with this 8. So we can essentially look at this as a negative 1 times 8 to the 3rd. So to make this easier on all of us, a negative times a positive is simply a negative. And then an 8 to the 3rd times an 8 to the 7th, well, you keep the base and add the powers. Again, because that power was directly associated with that base inside the set of parentheses, we're not actually impacting that negative at all. Okay? And then we just think about it as a negative times a positive. Having said that, let's continue with number 4. So we have m to the 9th, that takes care of that. Let's take care of our n's. So n to the 1st, n to the 2nd, n to the 4th. So altogether, that is n to the 7th. Okay, beautiful. Here's the issue. We have a negative 2 to the 3rd. We have a 5. And we have a negative 3 squared. Recall that because the power is not on the outside of the set of parentheses, that 3 is only being applied to the 2. So I like to circle it. Let's look over at the negative 3 squared. Same scenario. that 2 is not outside of the set of parentheses. It's inside with the 3. So the 2 is only being applied to base 3. We can rewrite this. So this becomes negative 2 to the third power is going to be 8. We still have our 5. And 3 to the second power is 9. And now all we have to do is move from left to right. So we have a negative 8 times 5 times negative 9. When you punch in from left to right, again, notice a negative times a negative is definitely a positive. But even as you punch this in from left to right, you get a positive 360. And that is how we would tackle a problem like number 4. Our strategy is maybe, if you like, we can work with the variable bases first, and then we can tackle the numerical bases afterwards. But the gist behind product rule is you must keep the base and then add the powers. Thank you, Keith, for asking that question. That's a wonderful question. Now let's look at the quotient rule. The quotient rule is super interesting because essentially what's happening here is that you're going to keep the base again, except you're going to subtract the powers and you're going to leave the difference where it's heaviest. What the heck does that mean? Well, if there are more in the numerator, then the difference will remain in the numerator. If there is more in the denominator, then the difference will remain in the denominator. What does that mean? Let me show you. So first off, the general rule is that if you have x to the m over x to the n, what you're going to do is you're going to keep the base, which is x, and you're going to subtract the powers, m minus n. Naz, I hope that helps. So we have m minus n, you're going to keep the base, subtract the powers. So I want you to take a look at this guy, and I'm going to leave it expanded. So notice we have x to the fourth power, there's 4 factors of x. Y to the second power, there's 2 factors of y. In our denominator, we have 2 factors of x, so x squared, and we have 5 factors of y, or y to the fifth. Now, I'm going to write this out twice. So first off, this is in exponential form. We will write this as x to the fourth, y to the second, over x to the second, y to the fifth. Do you agree that those are the exact same expression? Okay. Now check this out. Let's recall something that you're used to. Recall the fraction 3 over 9. If you had a fraction 3 over 9, all of you would say, reduce that. How do we reduce that? You would say, well, we would divide out a common factor. Okay, so you would say that we would divide both by a 3. If you divide both by a 3, you get 1/3. Another way to look at 3 over 9, and again, I'm going to put this here, is to say, well, isn't that just the same as 1 times 3? And this is the same as 3 times 3? And if that's the case, couldn't you divide out the common factor? So again, you're left with 1/3. That idea does not change when we're looking at the quotient rule. So I want you to notice that x divided by x, these cancel each other out. Let's do it again. Notice we have another set of x's that can cancel each other out. So you're essentially dividing out the x from both the numerator and denominator. Just one factor here and then one factor here. Let's look at our y's. We can cancel out one factor of y here, and we can cancel out one factor of y here. When all is said and done, notice you only have x's in your numerator and you only have y's in your denominator. So essentially, what we have left is x to the second power over y to the third power. Cool, that was pretty harmless, right? That was pretty straightforward. But that's in expanded form. What if I had like x to the 50th? You're not going to write 50 x's. That's crazy. So in this case, let's apply the quotient rule, but be careful with this. We don't want to leave any negative exponents. If we had a negative exponent, we would actually have to apply the negative exponent rule. So why apply 2 rules when we can simplify and just apply the 1? And I'll show you how we would do this. So notice here you have 4 factors of x in the numerator and only 2 x's in the denominator. When we cancel out 1 for 1, you're going to be left with 4 minus 2, which is 2 factors of x where it's heaviest. There are more x's in the numerator, so it would make sense that you'd have 2 left over in the numerator because there were more of them up top. Then take a look at our y's. They have the same base. This is a quotient rule, so we have to subtract the powers, but think of this logically. If you have 2 factors of y in the numerator, but 5, so many more, but you have 5 in the denominator, when you cancel 1 for 1, you're going to be left with 5 minus 2, which is 3 of them, but in the denominator. So by simply saying where would they be left, you're avoiding the whole negative exponent rule. And again, we'll see that in a little bit. Let's take a look at a few more examples. Okay, number 1. We have 16x to the 3rd, y to the 5th, m. And then we have over 22x to the 4th, y to the 10th, m. Let me see if I can bring this in just a touch so that it's easier to see. Hopefully that's a little bit more helpful. We can start with our variables first, just like we did with the product rule, if you find that that would be helpful. So if we start with our variable terms first, what we're going to notice is that, and again, I'm going to leave it as a fraction. If it's not a fraction, we'll fix it later. We'll start with the variable terms. We have x to the 3rd in the numerator and x to the 4th in the denominator. Notice that when you subtract these, you're going to have 1 left over, but it's heavier in the denominator, so you're going to leave that 1 in the denominator. That takes care of my x's. With my y's, I have 5 y's in the numerator, but I have 10 in the denominator. So when I subtract this, 10 minus 5 is 5. It's heavier in the denominator, so we leave it here in the denominator. Notice my m's will end up canceling. M to the 1st divided by m to the 1st is 1, so that's gone. Next, we have the 16 and the 22. Well, reasonably speaking, if I had 16 over 22 and I said, hey guys, that's the answer to my problem, you would say, no, it's not, you can reduce. You would say, let's reduce by dividing out a 2. If I divide out a 2, I'm left with 8 over 11. So let's put the 8 in the numerator and the 11 in the denominator, and you're done. The idea of reducing fractions in the way that we used to doesn't change just because we have a bunch of variables associated with it. It's still a fraction, and we still have to simplify. Okay? Yes, exactly. Now, wherever it's heaviest, that's where you're going to have the remaining factors, right? It only makes sense. So let's try number 2 and do the same exact thing. Again, I'll start with the variable bases first. It just kind of tends to be nicer this way. So I have an a to the 4th in the numerator and an a squared in the denominator. 4 minus 2 is 2. That means you're going to be left with a squared in the numerator because it was heavier up top. Chelsea, you asked a question about the m's, or Cece. The m's will cancel out because m divided by m is 1. So these actually cancel each other out. Think of the idea of having, for instance, what if I had 4 divided by 4? Wouldn't you say 4 divided by 4 is 1 because they cancel each other out? That's the same idea with the m's. So back to this one. A to the 4th over a squared, you're left with a squared in the numerator. We have b to the 7th over b to the 1st power. Remember, if there isn't a power written, let's write 1. So if you have 7 b's in the numerator and only 1 in the denominator, 7 minus 1 is 6, and you're going to be left with 6 of them in the numerator. Next, we have this fraction, negative 35 over 15. So let's take a look at it on this side. Negative 35 over 15. Well, right off the bat, if you were trying to reduce this fraction, you would say, I'm definitely going to divide by 5. So if we divide each by 5, that gives us negative 7 over 3. So let's put that right back into our fraction. Negative 7 over 3. And you've just finished simplifying number 2. Let's look at number 3 together. And I want to do all of these together because you have enough practice in Lumen where you can really get the hang of this. But I want to ensure that we cover all the different types. All right, same thing with number 3. Let's start with the variable bases first. We have a to the 11th over a to the 3rd. 11 minus 3 is 8. So you're going to leave a to the 8th in the numerator because it was heaviest up there. We have b to the 2nd over b to the 4th. 4 minus 2 is 2, so you're left with b squared in the denominator. Now let's take a look at that 5 to the 3rd over 5 to the 5th. Just like when we expanded this, I want to show you what it looks like expanded. 5 to the 3rd is 5 times 5 times 5. 5 to the 5th is 5 times 5 times 5 times 5 times 5. I'm so glad I did not make that like 5 to the 10th. When we simplify, we know that we could divide out common factors. Well, take a look. 5 divided by 5, those cancel. 5 divided by 5, those cancel. 5 divided by 5, those cancel. And you're left with 2 5s in the denominator. But what is 5 times 5? 25. And there you have it. If you wanted to rewrite this and say that that was 5 squared, I'm okay with that, except just like our previous problems, if you can evaluate, you should. 5 squared is 25, so we should write it in its simplified form. All right? Beautiful. So for the product rule, you keep the base, add the powers. For the quotient rule, you keep the base, subtract the powers, and leave it where it's heaviest. This way we can avoid negative exponents. Time to look at the extended power rule. I really like the extended power rule because we are already so used to the idea of distributing to drop parentheses. So for instance, let's recall something. Let's recall having, we'll do 8 parentheses, 3x minus 4, something like this, right? Notice there are no powers here. But if you had 8 parentheses, 3x minus 4, wouldn't your gut instinct be to distribute, to drop parentheses? It would be. It definitely would be. So you would say here that you're going to multiply. And you would say 8 times 3x. But in essence, what you're actually doing is taking the coefficient 8 and multiplying by the coefficient 3. Don't you agree? So it's 8 times 3x, or 8 times 3, which is 24x. So this becomes 24x. Same thing here, 8 times a negative 4, that's going to give us a negative 32. The idea of the extended power rule is that we are going to do the same thing, except this time, instead of distributing a coefficient, we're going to learn how to distribute a power. Distributing a coefficient, distributing a power. Similar concepts. So for the extended power rule, you're going to keep the base, and then you're going to multiply the power by the power outside of the parentheses. So for instance, you're essentially going to distribute the power to the other powers. All right, so you multiply power times power. Notice here, never multiply the power by the base. So when I show you a couple examples, I think you can understand what I mean by that. Let me dissect this first. Notice we have x to the m times y to the n, and the entire thing raised to the a power. The power of a. There we go. You're going to take that a, that power on the outside, and you're going to distribute to each of the powers inside. So that leaves you with x to the m times a, y to the n times a. Notice that a similar thing happens with our second expression. You have x to the m over y to the n, no big deal. take that power on the outside and you multiply power times power. So we distribute m times a, x to the m times a, over y to the n times a. For clarity and to make sure you're understanding this, our first expression, 7 to the second times 7 to the third, this is the product rule. Okay? Notice each base has its own power and you're multiplying them. So if each base has its own power and you're multiplying the bases, it's 7 to the second times 7 to the third. Keep the base, add the powers. But when we have 7 to the second raised to the third power, now we have the power rule. And didn't you hear it? 7 to the second raised to the third power. So this entire expression is being raised to the third. So what that means is you're going to take this 3 and multiply it by that 2. Power times power. So this becomes 7 to the 6th. Okay, I'm going to write power times power. That's the main difference between the two. You should be able to look at these and say, oh yeah, that's the product rule and that's the power rule. Remember, every base has a power. So when we look at number 1, it should be clear how we would progress through this problem. So let's take a look. We have 4 to the first power. Notice how I write a 1 in there. 4 to the first power, m to the 5th power, n to the 12th power, all raised to the third. Again, we are going to distribute that power of 3 to all the powers. So this is essentially going to say 3 times 12, 3 times 5, 3 times 1, power times power, power times power, power times power. So if we distribute the 3 power times power, we get 4 to the third, 1 times 3, m to the 15th, 5 times 3, n to the 36th, 12 times 3. Let's take our calculators, if you would like, and punch in 4 to the third. If we take 4 and we raise it to the third power, it's 64. We can totally write that answer in. So let's simplify further by saying this becomes 64 m to the 15th, n to the 36th power. Beautiful. Let's look at a few more examples. And again, repeat after me, power times power, power times power. Let's take a look at number 2. For number 2, we have a -3. Notice that 3 doesn't have a power written, so let's write 1. And actually, you know what? I'm going to rewrite this. I'm going to make this a little bit bigger. So we have -3 to the first power, x to the 11th power. That y does not have a power written either, so we're going to write y to the first power. And this entire expression being raised to the 4th power. So this is definitely the power rule. According to the power rule, we're going to do power times power. So we're distributing power times power, power times power, power times power. Now here's the other piece that I want you to consider. What in the heck do we do with that negative? Think about this logically. That negative is inside this set of parentheses, correct? And the set of parentheses is being raised to the 4th power. So let's think about this logically. A negative times a negative times a negative times a negative. Negative times a negative, positive. Negative times a negative, another positive. Positive times positive, positive. So anytime you have a negative quantity raised to an even power, it's got to be positive because every pair of negatives is positive. So this -3, when it's being raised to the 4th power, that negative times a negative times a negative times a negative becomes positive. And then we have 3 to the 4th power, 1 times 4, x to the 44th power, 11 times 4, and y to the 4th power, 1 times 4. Same thing with that 3 to the 4th. If you punch that into your calculator, 3 to the 4th is going to give you 81. So let's write our answer as 81, x to the 44th, y to the 4th. If that idea about the negative being raised to the fourth power is still tripping you up, check this out. Do you agree that negative 3 to the fourth power, just like I have written here with parentheses, would be rewritten as a negative 3 times a negative 3 times a negative 3 times a negative 3? Nobody says you can't rewrite it so that you can see it better. Why not? Why not, right? That negative 3 is inside of the set of parentheses, is being raised to the fourth power, so why not rewrite it and see what it looks like? When you move from left to right, negative 3 times a negative 3, that's a 9. Negative 3 times a negative 3, that's another 9. 9 times 9, 81. So that's another way to see that our result is in fact accurate. Based on what we discovered here for number 2, I put this note in your guided notes that says if we raise a negative quantity to an even power, then it becomes positive. If we raise a negative quantity to an odd power, then it becomes negative. So here you have the example, negative 1 to the 6th power is equal to 1. Well, that's true, because negative 1 times a negative 1 times a negative 1 times a negative 1, and so on and so forth, when you combine those, it'll give you a positive 1. But when you have negative 1 and you raise it to the 5th power, and I'll just rewrite that so you can see it, 1, 2, 3, 4, 5, notice that negative 1 times 1 is 1, negative 1 times 1 is 1, but you still have that negative 1 there, so it stays negative. I wanted to show you this example and write this statement out before we saw number 3, because I want you to be really careful. Notice with number 3 where the negative is located. Do you see that the negative is in front of the set of parentheses, which means that it's not inside the set of parentheses, which means that that power of 10 does nothing to it? It is this idea that if I had negative 3 squared, my answer would actually be negative 9, because the only thing I'm applying that to, that power of 2, to is the base 3. So that negative stays. With the number 3, we know our answer is going to be negative. That negative is going to stay. What our focus should be on is what's happening here inside the parentheses and then with that power. For number 3, we have a special example here. For number 3, we have 2 rules that we're going to apply. We're going to apply the quotient rule, and we're also going to apply the power rule. We know we're applying the quotient rule because we have common bases, numerator and denominator, common bases, numerator and denominator. And notice the 6 over 54 we can definitely simplify. So the first thing I'm going to do is I'm going to look at what's inside the set of parentheses, right? Think PEMDAS. Personally, I find that it is helpful to work from the innermost set of parentheses outwards, just like we discussed with the order of operations. And in this case, it's easier to simplify inside the set of parentheses, think P and PEMDAS, before applying the exponents. So I'm going to write PEMDAS above this. And we're going to take care of what's inside the parentheses first. So if we look at just what's inside the set of parentheses, I'm going to rewrite this. We have a 6b to the 12th, c to the 1st, and we have a 54b to the 3rd, c to the 9th. Okay, let's apply the quotient rule here. We'll start with the variable bases. We have a b to the 12th over b to the 3rd. When I keep the base and subtract the powers, b to the 12th over b to the 3rd, 12 minus 3, well, that's 9. And it's going to be left in the numerator because that's where it is heaviest, so b to the 9th. Let's take a look at the c's. For my c's, I have c to the 1st over c to the 9th. Quotient rule says we subtract the powers. 9 minus 1 is 8. And it's going to be left in the denominator because it's heaviest in the denominator. Next, notice I have a 6 over 54. So if you want, we can rewrite that and look at it clearer. So if you have a 6 over 54, notice you can divide both numbers by 6. 6 goes into 6 once, and 6 goes into 54 9 times. So we can put 1 here. Twiggy. Sorry, my puppy's playing around. So we can place the 1 in the numerator and the 9 in the denominator. The entire expression inside the set of parentheses is now simplified. We still have a negative in front, and we still have that power of 10. So once we finish that quotient rule, it's time to now use the power rule. This particular section of the video you may want to watch again to ensure that you're understanding the flow through a problem like this. In Lumen, you'll see a bunch of examples like this, so you can rewatch this part just to make sure you're understanding everything that's happening. But notice the idea is simplify inside the set of parentheses, the P and PEMDAS. Simplify inside if you can, and then apply the power rule. Exponents, right? Power rule. So Christine, the rules are different. Notice here we have a fraction. So when you have a fraction, that is the quotient rule. Notice you have common bases. They're both a numerator and denominator. If, for instance, and I'm sorry, I'm going to leave this for a moment. If, for instance, you had, and I'm going to write this down here, what if you had 3x to the 5th, y to the 2nd times 11x to the 3rd? This is the product rule. So 3 times 11 is 33. And then the product rule says you keep the base, add the powers. That's the difference. You have to recognize that this is not a fraction, right? So because this is not a fraction and they're all on the same level, these are all in the numerator, x to the 5th times x to the 3rd, well, you keep the base, add the powers. And didn't we say x to the 5th times x to the 3rd? We'll bring down the y squared, and that takes care of this guy. But if you look at our fraction, we have b to the 12th over b to the 3rd. That's the quotient rule. So a fraction versus non-fraction. So at this point, let's apply the power rule. Power times power. This 1 is being raised to the 1st power. This b is being raised to the 9th power. This 9 is being raised to the 1st power. And the c is being raised to the 8th power. So you're going to take power times power. Every power gets multiplied by 10. So my answer becomes a negative 1 to the 10th, b to the 90th, over 9 to the 10th, c to the 80th. Now there's only one thing I will simplify, and that's here. 1 to the 10th is simply 1. So I'm going to write my answer as negative 1, b to the 90th, over 9 to the 10th, punch that into your calculator, c to the 80th, and then we're done. All right. We still have 2 exponent rules left, but I'm going to stop at this point. Okay, guys, so tomorrow's class will finish the 0 exponent rule and the negative exponent rules. Those will actually go very, very quickly. So when we multiply polynomials and we divide polynomials, that's going to go really quickly, which means we'll be ready to start factoring. So I will email you the Unit 7 notes so that you're ready for when we actually move into factoring. Today's Wednesday, so tomorrow we'll finish these notes. And on Monday, this upcoming Monday, when your homework is due, we will start factoring, okay? Wonderful job, guys, today. I love the questions. They were so helpful. Stay safe. Stay healthy. I will see you guys tomorrow for our last class for week 11. Crazy. Bye, guys.